buffers. Why are we talking about them? Why do we pay so much attention to them? Why do we make you work on them even though it may be initially difficult and hard to understand? Well, because buffers have an extreme importance in all biological systems. For example, our blood is a buffer. In our bodies and in a lot of other living organisms, buffers are tasked with preventing wild fluctuations in pH values in our body. And so, first, of course, is the definition. Buffer is a solution that is prepared to resist pH changes, even if a small amount of strong acid or strong base is introduced. In other words, living organisms prefer neutral environment, pH of 7 or close. And when that pH gets disturbed, if somehow acid or base gets in the system, that can cause cells to quickly die. And so buffers are very important because they prevent those fluctuations from occurring. So how does one make a buffer? Well, there are two ways. One most common is combining a weak acid with the salt of that acid. In other words, the buffer must contain an acid, a weak acid, and the conjugate base of that acid. Less common possibility for making a buffer would include combining a weak base with the salt of that base. In other words, weak base plus conjugate acid of that base. Let's consider some examples. I mentioned carbonic acid before, and we talked about sodium bicarbonate. If we combine a weak acid such as carbonic acid with sodium bicarbonate, that includes bicarbonate ion. Bicarbonate ion, of course, is a conjugate base of carbonic acid. We get, in the combination of these two substances, we get a buffer. This buffer is the one that's in our blood. So we have sodium bicarbonate in our blood, and we have some carbonic acid in our blood. And so this is the buffer, this particular two substances is what's preventing pH of our blood from changing quickly should it be exposed to a strong acid or strong base. For buffer in example B, we could potentially look at a buffer prepared by combining ammonium hydroxide, a weak base, and ammonium chloride. Ammonium chloride, of course, contains NH4+, which is a conjugate acid of ammonia, and so NH4OH and NH4Cl would be considered a buffer as well. So how do we find pH of a buffer? Hopefully you've looked at this in lecture previously. So-called Henderson-Hasselbalch equation. pH of a buffer can be calculated as pKa of the acid used to make the buffer plus log, this is log with a base of 10, of a ratio of conjugate base to the weak acid concentration in that particular buffer. Couple of things to point out here as far as this equation. You are not, at least for lab, expected to memorize it. If there is a question using this equation, say on the lab final, I will give you the equation. What you do need to know, though, is a couple of things. First of all, this equation can only be used to find pH of a buffer. So before you use it, you want to make sure that the system you're looking at actually does constitute a buffer. Second of all, what people often forget is what pKa stands for. pKa is not the same thing numerically as Ka. In fact, pKa is negative log of Ka. So keep that in mind. So usually Ka for acid used to make a buffer would be given to you, so you have to remember to take negative log of that to find pKa. So whenever you see P in front of any sort of symbol like this, remember it's negative log of that value. Sort of like pH is negative log of hydronium ion concentration. So how do we use Henderson-Hasselbalch equation for finding pH of a buffer? So let's consider a hypothetical buffer prepared by using 0.2 molar acetic acid and 0.5 molar sodium acetate. Well, first we need to know the Ka, so Ka should be given. Ka for acetic acid is 1.8 times 10 to negative fifth, so pKa can be found as 4.75. So then we can go ahead and find pH of this buffer by taking pKa of acetic acid, which is 4.75, plus log of the ratio. This is acetate, the conjugate base. On the bottom here is a weak acid, acetic acid. So where's concentration of conjugate base is going to come from? Well, right there, sodium acetate is the source of acetate ion. So the concentration of conjugate base would be 0.5 moles per liter. What about acetic acid? Well, acetic acid clearly is present in a concentration of 0.2 moles per liter. So 0.2 will be in the denominator for our equation. So 4.75 is pKa plus log of the ratio of conjugate base to the weak acid concentration. By doing the math, we get value of 5.15. I suggest you do this problem on your own to make sure you get the same numerical answer as I did. So how are we going to make buffer in lab? I'm just going to show you some calculations first, and then I'm going to show you how I actually make that buffer. So if you look at your lab manual, page 144, part 5, it says preparing a buffer solution. And on step 20, it says add 2.0 grams of solid sodium and solid anhydrous, meaning not containing any water, sodium acetate. So what if we took 2 grams of sodium acetate? We could easily find how many moles that would be. Molar mass of sodium acetate is 82 grams per mole, so we take 2 grams times 1 over 82 grams, grams cancel, we get 0.024 moles of sodium acetate. Then on the next step in your procedure, step 21, it calls for 4.0 milliliters of 6 molar acetic acid. So we have volume and we have molar concentration. We convert milliliters to liters, that gives us 0.004 liters. We multiply by molarity, which is 6 moles per liter, we get 0.024 moles of acetic acid. And then the procedure, if you read further, calls for combining the solid sodium acetate with 4 milliliters of 6 molar acetic acid. And as you can see from my calculations, the moles of acid and the moles of base in this particular buffer would be equal. And then you would add 46 milliliters of water to create a total of 50 milliliters of the buffer. So both of these quantities of the salt and the weak acid would be present in the same volume of 50 milliliters. That suggests to us that concentration of the weak acid would be equal to the concentration of conjugate base in that resulting solution. So how do we calculate pH of that buffer that we're going to make in a minute here? Well, we take pKa for acetic acid, which was still 4.75, and then I didn't use concentration here, I just used moles, because I know these moles are present in the same exact solution, the same exact volume. And what you see here is because my moles are the same, they're going to cancel, and I'm going to get log of 1. In math, log of 1, log with a base of 10, log of 1 is 0, and therefore pH of this buffer would be equal to pKa of the acid. This, in fact, is a very important thing to remember. pH of any buffer that contains equimolar concentrations of acid and the conjugate base of that acid would always be equal to pKa. So whenever you look at the problem and it talks about a buffer where concentration of the weak acid and the conjugate base are equal, you don't even have to do much math, you just have to find pKa of the acid, and that will give you pH of that particular buffer. So next, let's consider what you're supposed to do next, and that's what I'm going to do shortly to show you the actual procedure. So it says add 50 milliliters of water, right? So, I'm sorry, 46 milliliters of water to create 50 milliliters of the buffer. And then it says on step 25, using a graduated cylinder, add 25 milliliters of the buffer each to beakers 2 and 4. So basically what it's telling you to do is split your buffer into 2 equal portions, 25 milliliters each. And then on the previous step, on step 24, it basically asks you to have 2 beakers, each filled with 25 milliliters of water. So total of 4 beakers, right? 2 contain 25 milliliters of buffer. The other 2 would contain 25 milliliters each of DI water. And then on steps 27 and 28, you're supposed to add small amount, 0.5 milliliters of 6 molar strong acid, or same amount of strong base each to beakers with buffer and with water. So why are you told to do this? It's always a question, why am I doing something, right? Well, the purpose here is to compare what happens in the buffer when you add strong acid or strong base to it versus what happens in DI water. So let's take a look at what happens in the buffer first. So procedure tells us to measure 25 milliliters of the buffer and then add to it 0.5 milliliters of 6 molar HCl. Of course, HCl is a strong acid, we talked about it a million times. Therefore, we can find how many moles of hydronium ion would be added. So this is our 0.5 milliliters expressed in liters. This is molarity of the acid we're adding. That gives us 0.003 moles of hydronium ion. Now, this is the buffer, right? This is the buffer we're going to make. To make the buffer, we will be combining acetic acid with sodium acetate. We have to figure out here what happens when we add our hydronium ion from HCl to this combination of the chemicals. Remember, buffer is not one substance, it's actually 2. And you must, I repeat, must pick which of these 2 will react with hydronium ion. So how do you do that? Well, let's think about this. This here is acetic acid, it's a weak acid. Is it possible that a weak acid will react with another acid such as hydronium ion? No, we never see reactions between 2 acids. However, what about acetate ion? Acetate ion is a conjugate base of a weak acid. The rule that I hope you've learned before is that the weaker the acid, the stronger the conjugate base. In other words, because acetic acid is weak, acetate ion here is basic. It's expected to have some basic properties. So only acetate in this instance is expected to react with hydronium ion. Only acetate. So how do we write the chemical equation for this then? Acetate ion from the buffer is going to be reactant. Another reactant is the HCl we added that created hydronium ion. Remember, Bronsted theory comes in handy. This is going to be our acid. Acetate acts as a base. Proton is transferred from the acid to the base. You get water and you get acetic acid. Now, you notice these red arrows. What are those for? Well, these are designed to predict how the concentrations of the buffer components will change when we add a strong acid to our buffer. This is the strong acid we added to the buffer. This and this were initially components of the buffer. So sodium acetate or acetate ion in this case is acting as a reactant. Concentration of a reactant is expected to decrease as the reaction progresses. So concentration of acetate would be expected to go down. Acetic acid, which was also present in our buffer to start, is a product in this equation, and so the concentration of the product is expected to increase, and in this case, concentration of acetic acid is going to go up. So ice table, initial, change, and. One important point, when we're talking about buffer, we have both acetate and acetic acid to start. So typically when you do ice table, you don't have any products, you have a 0 here. But buffer is different because you have both. of these substances in your solution. Now, how did I get 0.012? You might be wondering where I got 0.012 from. Well, let's say we prepared our 50 milliliters, or will prepare shortly, 50 milliliters of buffer solution by combining 0.024 moles each of acetate and acetic acid. But then we cut that amount in half. We will be separating the 50 milliliters into two 25 milliliter portions. And so that's where 0.012 comes from. Notice these are not concentrations, these are number of moles. I decided to keep it as number of moles because it makes math easier. So if you take 0.024, split it in half, you get 0.012. So these are moles of acetate. In 25 milliliters, these are moles of acetic acid in 25 milliliters of the buffer. Where did I get 0.003 moles for hydronium ion? Well, 0.5 milliliters of 6 molar HCl gives us 0.003 moles of hydronium ion. So we add this amount, immediately acetate will be reacting and this will cause a reduction in the number of moles of acetate by 0.003, because that's how much is needed of acetate to react with hydronium ion. And all that acetate is then going to be converted into acetic acid, so the amount of acetic acid is going to increase by 0.003 moles. So what are we going to have in the end? Is there any hydronium ion left? The answer is no, because as you can see, hydronium ion is by far limiting reactant. It's present in much smaller amounts, so it's gonna completely get used up and its concentration is gonna go to 0. How much acetate is gonna be left? We started with 0.012 moles. We used 0.003 moles of it for the reaction with hydronium ion. Therefore, we're left with 0.009 moles. Just like we predicted, the amount of acetate has gone down compared to how much we had originally. What about acetic acid? We started with 0.012 moles, 0.003 more moles of acetic acid was formed as a result of a reaction. So we have to add these two, and we get 0.015 moles as a resulting amount of acetic acid. So how is that reflected in our Henderson-Hasselbalch equation? Well, right here. pH of the buffer after we add acid to it is found as pKa plus log of the ratio of acetate to acetic acid concentration. Now these two concentrations are not the same anymore because one went up, the other one went down. Acetate, as we saw, went down to 0.009. Acetic acid, as we saw, went up because it was a product to 0.015. So now our log will be over ratio of 0.009 divided by 0.015. So you can hopefully do that math itself. Once again, a reminder, concentration of base decreases when we add a strong acid to the buffer. Concentration of the weak acid in the buffer will increase because that weak acid will be a product in the reaction. So now let's take a look at what we're actually doing here. So in this weighing boat here, I have 2 grams of sodium acetate. It's anhydrous, meaning it doesn't contain any water in it. I'm going to add it to this beaker here. Make sure I transfer all of it. And then I already pre-measured to save time. This is 4 milliliters of 6 molar acetic acid. So I'm basically just following the directions in your lab manual, starting with step 20. So 4 milliliters of 6 molar acetic acid. I'm going to go ahead and add this acid to my acetate. So next it calls for 46 milliliters of water. Why 46? Because solid is not assumed to occupy any volume. 4 milliliters of acetic acid plus 46 milliliters of water will give us 50 milliliters total of our buffer. So I'm going to measure out, do it a little faster. So you can see here, can get rid of the stubborn bubble, but hopefully you can see I got 46 milliliters of water here. I'm gonna add this to my solution. I have to use a stirring rod here to stir up my sodium acetate to make sure the solid is completely dissolved. It dissolves really well in water, so I shouldn't have any problem. See, it quickly dissolved. So what do I have here now? Here in this beaker I have 50 milliliters of my buffer. So what did the procedure tell us to do next? Well, it told us to split this buffer into two portions of 25 milliliters each, right? If we want to come around here, I already have two beakers with 25 milliliters of water each. I thought I had my beakers ready, but can't find them. Here real quick, I'm gonna rinse them out. So this is my buffer. I have a clean graduated cylinder here. So I'm going to measure 25 milliliters of this buffer. So remember, we have to divide it basically in two equal amounts. We prepared 50 total, so I have 25 here. I'm gonna pour it into this beaker, and the other 25 milliliters will go into this beaker. So now, buffer, I know why, couldn't find the beaker because I forgot to label them. So this is my buffer here, and this is my water here. So I'm going to take these two over here. In this container here, in this glass bottle, I have 6 molar hydrochloric acid. I'm going to use the bulb to fill the 5 milliliter pipette with 6 molar HCl. Now, remember, the directions call for 0.5 milliliters of 6 molar HCl to be added to each 25 milliliters of buffer, that's this beaker, and 25 milliliters of water, that's that beaker over here. So that's what I'm going to do, 0.5 milliliters only, so it's not really very much. I'm gonna so that's 0.5 milliliters, and then another 0.5 milliliters into this one. I'm going to stir. And then we're going to move over here where my pH meter is. First though, this is my original buffer, my other 25 milliliters. So first we're going to measure pH of just the buffer, nothing added to it, just the buffer we prepared. Use the electrode really well, shake off the water. So this is original buffer. Remember when we did our calculations, for pure buffer, we predicted that this buffer pH would be equal to pKa of acetic acid, and I believe our calculation gave us 4.75. What we're seeing here for this buffer is 4.61. So in your report sheet, where it says original buffer measured pH, please record 4.60. So now, I'm gonna set this aside. Here's my electrode. Take off water. So this now is the buffer, but in this case we added 0.5 milliliters of 6 molar HCl. Let's see what we get. So what we are seeing here is that pH of the buffer did go down, but it didn't go down by much. We started at 4.6 something, 4.60 I believe, or 4.64 maybe for pure buffer. This is the buffer with added strong acid, and pH went down to 4.21. So where it says buffer with added HCl for measured pH, please record 4.2. It looks like 4.22. 4.22, 4.21 doesn't matter really. Close enough. What do you think will happen when we measure pH of water to which we added HCl? That's an interesting question. So we added strong acid to water. We didn't add much of strong acid, but this is water with added acid. We perhaps should start with measuring pH of just water. So I have some dry water here. And pure water, the expected pH for it, theoretical pH would be 7. This seems to be a little bit on the low side. Maybe I should just get some pure water here and dump this out. Maybe my beaker and some more water. So it's quickly rising. My guess it would probably go up to very close to 7, maybe check something real quick. So dry water would be close to 7. I just don't have time for it to keep going up. It will probably be going up. Maybe not, but let's take a look at water with acid. So this is water with 0.5 milliliters of HCl added to it, and pH went down all the way to 1 point. Looks like it's still going down. I'm not gonna wait too long. So it looks like 1 point. Let's go with 1.46 or 5 or 4. So something like 1.4 would be the pH for water with buffer. That's it for now. We'll take a look at the base added to water and buffer next.